So in our second video today, I'll take a look at then, similar to our first video, how do I take the derivative of any logarithmic function? For example, here I've written out a logarithm with a base of 8. So far we've investigated is ln x, which again is the logarithmic function, but that base number is e. So first our theory will develop what is our rule for this. So if I look at some random logarithmic function, y equals log base b of x. Few restrictions with logarithms. Don't forget that the base has to be a positive number and it's not allowed to be 1. The argument of a logarithm always has to be positive, so x is greater than 0. To develop a rule for this one, what I have done is I've switched from logarithmic form to exponential form. Remember that the base of a logarithm becomes the base of the power. The answer to a logarithm is the exponent on that power, and the argument becomes the answer to that power. What I'm going to do here then is, since we just developed a rule for any exponential function, is I'm going to now use that rule on the left-hand side. If I take the derivative of any exponential function, I get the exponential function again, multiplied by the ln of the base, in this case that is base b, and because our variable is y, then I have to multiply by the derivative of y, so dy by dx. Again, that's our chain rule idea. On the right-hand side, the derivative of x is just 1. If I rearrange, we have dy by dx is 1 divided by this stuff, by ln b. And then again at the end, we make a quick substitution, and that's that by, b to the exponent y is equal to x. So in this case, we see that this is very similar to our natural logarithmic function, where if this was ln x, the derivative would be 1 over x. Because now we've extended this to logs with any base, this becomes 1 over x, but the x gets multiplied by ln of the base. And again, I've written this out in general here. And in red, I just wanted to show you that, again, this rule does work for our natural logarithmic function as well. If f at x is ln x, then the derivative using this rule would be 1 over x ln of the base. This base happens to be e, and what we would see then is that ln e equals 1. So this natural logarithmic function derivative is actually a really specific case of this more general version. So a few examples we'll work through, and then time for you guys to try it on your own. So if I take the derivative here, I would get y prime equals. The derivative of any logarithmic function is always going to be 1 over the argument. So 1 over x to the exponent 4. The new part is that we now need to multiply by ln of the base. So ln 8. And then we multiply this using our chain rule. So that's the derivative of the outer function. I now need to take the derivative of the inner function. So we would multiply that by 4x cubed. Simplifying here, this one does simplify nicely. We can divide out the x cubed with 3 x's here. So we would end up here with 4 over x ln 8. In the second example, again, this idea that we can now combine this rule with some of our other exponential rules, derivative rules. What we should see here is that we have a product of two functions, so I'm going to have to use our product rule. Derivative of the first is 2x multiplied by the second, which is log of 2x, plus our first function, x squared, multiplied by derivative of the second function. So we would have 1 over the argument, so 1 over 2x, multiplied by ln of the base. We need to be a little bit careful here. Reminder that when we have a log that does not have a base, that the base is implied to be base 10. So we have to watch, because now that's important here as we take the derivative, because I have to take the ln of the base, and then I need to multiply that by the derivative of the argument, or the derivative of the inside here of the log, the inner function. So that would multiply here then by 2. Again, we're looking for some possible simplifying that could happen here. So if I want to simplify this here, the first part Doesn't really simplify a whole lot. We would end up with 2x log 2x. This part here we can clean up a little bit. We can see that the 2's would divide out. I can also divide an x with one of the x's here. So in the end, the second part, we end up with x over ln 10. And then when we have product rule, we often look for common factors. I don't know if this would necessarily be considered a whole lot more simplified, but if we want, we could common factor an x out here, and then that would leave us with 2 log 2x plus 1 over ln 10. In general then, if we have any logarithmic function, I've just chosen a base 5, any logarithmic function, and we have some other inner function here for taking the derivative, then we would end up here with y prime equals 1 over the argument, which in this case happens to be g at x, multiplied by ln of the base, in this case ln 5, and then I would have to multiply that by the derivative of the inner function, or the derivative of that argument, which would be g prime at x. Hope that helps. Let me know if you have any questions from the homework, and send me an email if you do, and I can respond back to you. Have a good day, guys.